Excellent. Well, thank you, Joshua, for that introduction. And thank you for the invitation to come and speak with you today virtually. It's 11 a.m. Where I am in central Maine in the United States. And I appreciate all of you spending your late afternoons, early evenings, depending on how you call it, with me here this afternoon, this morning, this evening, whatever it is. I do want to mention that I have all the slides and the code available that I'll talk about. And I just put a link in the chat that will take you to all those resources. And so don't feel like you need to write everything down, or don't feel like you need to copy everything as you hear them. All the resources that I'm talking about will be available there on that GitHub repository. And we can talk maybe more about GitHub when we get to the coding aspects of what I'll go over here this morning. It's a great resource for people doing statistics and coding and programming with forestry data, with other data sets as well. So I look forward to talking more about that. With that, I'm going to go ahead and share my screen. So you should see the slides nice and big on your screen. And I encourage you, if you have questions, type into the chat. I might prompt you all to type into the chat for those of you on Zoom. If you're streaming on another platform, I'm not sure how that works, but we can find a way, or I'm sure maybe Joshua can help connect us to learn about how we can help to answer your questions. And so the task today, kind of our mission, is to talk a bit about sampling design and statistics in forestry. And these topics are very, very large topics. There's no way, even over the course of the next 2 hours, we're going to be able to cover the ins and outs of all of them. So I think what I've put together is a pretty broad overview, but I think I'll mention certain things where you can dive deeper. And there are students that get PhD degrees in these topics, and so there's a lot of information in these topics. But I think what I'll provide is a broad overview in the slides, and then with the code to really give you some practical, on-the-ground application of using some of these concepts in the real world. So hopefully that will provide value to you. I did want to share just a little bit about myself. So I'm a forest analytics consultant. I help and support forest companies and organizations with data and analytics needs. A lot of that is related to things like understanding forest carbon. Many of you know that forest carbon is of interest to a lot of different people with climate change, with emerging forest carbon markets. And so I spend a lot of my time doing that. And my background is mainly forest biometrics, growth and yield, understanding statistical issues as they relate to forest resources and environmental problems. Before this, I was in academia for about 10 years, mostly at the University of Minnesota, where I did teaching and research and outreach to a number of people, mostly focused on forest health. And so in my research in that area, I tried to integrate kind of what I knew about forest biometrics and statistics into the areas of forest disturbances and forest health. And so my education's there. I did my PhD at the University of Maine. That's just up the road from where I am currently. My master's at Virginia Tech, and my bachelor's in a forestry school, a small school at Paul Smith College in upstate New York. So I wanted to share just a little bit about the trees that I see on a daily basis. So I'm located in central Maine. We're basically as far northeast in the United States as you can get. And so the forests are plentiful here in the state of Maine. You can see the map of the forest area in the US if some of you are unfamiliar with the area. But we're fortunate where I live in Maine to have trees literally in my front yard, backyard, everywhere around me. So we're right along the coast. So the Atlantic Ocean comes right up to the coastline of Maine, and the forest starts pretty much right away. So it's nice to see those kinds of forests. But then we also have mountains. Some of these mountains can get up to, I'm going to apologize here. I know many of you are probably more well-versed in the metric system. Myself, I use mostly the English units. These are about 5,000 feet is our highest one. So whatever, somewhere between around 2,000 meters plus or minus a few. So we have the ocean, we have mountains, we just have a lot of abundant natural resources where I live in the state of Maine. And so a little bit about the work that I do in my company. We generally, we just have a ton of information about our forest. We're collecting data all the time. We don't really have a good sense of what to do with all the data that we collect. And so that's really how I help to support companies and organizations, is to provide that analytics support. And so a lot of that includes the traditional forest biometrics work, things like understanding the volume and the growth and the yield of understanding different forest management treatments on some of the different silvicultural techniques that we might do. And then it also, like I said, doing a lot now related to forest carbon and what that means for landowners interested in enrolling, for carbon markets interested in offering a carbon for sale in the marketplace. And so all of this work really that I do is to help support organizations, to empower them to make decisions with some of their data sets. And so that's kind of the work that I do on a daily basis through my company. So a little bit of an outline, kind of a roadmap of where we're going here for the next 2 hours. I'm going to first share some slides that really focus on sampling in forestry. And so we'll talk about many of the common ones of kind of theoretical level. Here are the approaches, and then here are the applications. And then I want to show some R code that talks about the importance of stratification within sampling for, in our case, I'll use a forestry example, but it's really anything related to natural resources or anything else you might sample in the real world. And so I thought we'd take a short break after that and then go into the next session that covers more the statistics side of forestry. And so I'll talk about some common methods that we use in forestry, and then another R code session where I'll fit some tree biomass equations using some of the newer packages available in R to help do that. So I'm curious if you all have used R before. And so if you're on Zoom, I would encourage you, type into the chat, just type a 1 if you've used R before in any kind of project at all. Great, so seeing a couple of 1s. Great, a few more 1s coming in. That's good to see. Like I said, don't feel like I'm glad that there are people that may not have experience with R. Like I said, with the resources I provided, hopefully you can have a look back at those and just kind of save those, if you wanted to do some of this in the future. So yeah, no prerequisite that you have to learn R before this session, but you'll have those resources available to you if you wanted to visit those at a later date. So let's jump into talking about just some common sampling designs in forestry. Well, I think it's good to take a step back. We talk a lot about sampling in the real world a lot. You can think about it as, a survey is done for, do you support this political figure? Would you vote for this person or not? Yes or no? Do you support this new initiative that's this organization is undergoing? So sampling is obviously rampant in our everyday lives, and all of the information that we gain from those samples we use to make inference about the population of interest. And so in forestry, we just don't have the time, don't have the resources to measure every single tree or everything about the forest. And so we need to sample in an efficient way to better understand the attributes of a forest. And so here are a few things that make the sample good. Well, it needs to be unbiased. That means we need to take a good sample that represents that population. And so if we're interested in understanding pine trees, we aren't going to go out and measure all of the hardwood trees to try to represent those pine trees. And so we need to be unbiased in the way that we select our sample. We also need to have it be efficient. That is, it's easy to obtain data and the data representative of the population. Now, the term easy is a subjective one, but it goes to say that there must be ways that we can efficiently collect the kind of information that we want in a pretty efficient manner. And then the sample needs to be flexible. And so in this case, what I mean by that is that, well, we might go out and collect the data for a certain reason, say we want to make a new equation based on the data because we don't have a good equation to work with, say for predicting the volume of a tree. So we might need to go and collect those data, but it would be really nice if we could use those data in other applications as well. And so maybe down the road, if we need to fit a new equation, we might want to have our data to be flexible to answer more than just one objective. And so these are some attributes that you can think about and maybe think about in your own forest that you're familiar with, what might make a sample good. And so to do sampling, we need designs to do this sampling in an efficient way. And so all this means is that we need to specify some configuration of sample units and the method used to determine which units are selected. And so if we know that we have a 20-hectare forest, we don't just want to go measuring trees randomly. We could, and there's an approach for that, but we might want to be more selective in terms of how we sample those trees. And so simple random sampling is a valid and a useful way to sample, in our case, forests. But there are other approaches such as systematic sampling and then stratified sampling, which can include both random and systematic designs in their approach. And so this is a good example of how the importance of sampling designs is when we're looking at sampling forest resources. So to start off, we'll talk about simple random sampling. And in this case, it's every combination of a sample unit has equal and independent chance of being sampled. And so, for example, as you take a look at the grid here, this is a grid of just random points. Imagine these might all be forested plots that you might take an inventory of across a landscape. What you're seeing here is that all of these different points that are selected have been selected randomly. There's no pattern in these. Now, there may be clusters like we could see up here. Well, we're measuring 3 plots. They're quite close to one another. Maybe we might be concerned about that. But on the whole, these were sampled randomly. And so if your population is pretty much very similar, and so in the forestry context, that could be something like a plantation where you know you're working with one species of a similar age and a similar structure. Simple random sampling works really good. It's also pretty good if you don't really have any other information about the forest. And so if you're really kind of coming into a new area, or perhaps a company or an organization you're working for recently required a new tract of land and you don't really know anything about that land, well, simple random sampling really works really well. There's been a ton of statistical research done on this sampling design because it's so widely used. Now, there can be disadvantages to simple random sampling as well. And so, on the other hand, it can be very expensive and inefficient, especially when you think about what this means in the forest. And so for that, like going back to this cluster of plots, well, imagine if this cluster of plots was all in a very wet area where it took you, a long time to work your way in this area because there's standing water and it's very inefficient to walk around. And so if those plots are located in a terrible area like that, well, you can't really move them. By random chance, you have to sample those plots under a simple random sampling design. So it can take you longer to sample the plots. It can take you just more inefficiencies that you'll face if you do. It also sometimes doesn't ensure complete coverage of a target population. As an example, if we take a look at this area kind of in the lower part of the graph, there might be something interesting going on here, say in our forest, but we're not sampling there because by random chance, our sampling design doesn't pick any plots to sample there. And so that's an interesting disadvantage of simple random sampling. And then it doesn't really make use of any previous information about the forest. And so what I mean by that is that you can go and measure these things randomly, but you don't really necessarily need to know anything about the forest before you set up your design and before you begin to go out and sample. And so there are other approaches we'll talk about that make better use of some of that information. So take a switch now. Instead of simple random sampling, let's be systematic about how we sample. And so here are 2 examples of a systematic grid. And so this is oftentimes really easy to implement in the forest. And the goal of it is really to try to ensure that complete coverage spatially in the context across the grid. And so in this case, it's, well, every 100 meters, have a new line where you walk down, and then say every 50 meters, do a new forest inventory plot. And so you can kind of do this in a systematic way, and then you can basically be really efficient because you know how far apart each plot is from one another. And there are different ways to align your grid so that you have more sampling done in one line versus another. And this is a really good thing because it's more efficient. You don't have to travel as much between plots. You can often relocate the plots easier. And so if you want to go back to the plot and a year from now or 5 years from now to measure the same trees, it's often easier to find these because if you're on this grid pattern, you have an idea about where you might land. And systematic sampling is done often because it can help to delineate things that you see on the ground. And so in particular for areas where you have multiple stands, and so you have, say, a forest with that's a very low age, say it's recently planted 5-year-old pine trees, and then adjacent to that you have the 60-year-old hardwood trees. Well, by doing the systematic grid, you can almost begin to delineate where those boundaries are, depending on how intensively you sample across this grid. And so there's lots of advantages to doing a systematic approach like this. But there are also disadvantages like every sampling design. The big one is that the observations are not independent. That is, you're measuring these systematically, and so they're not necessarily independent of one another like they are in simple random sampling. Another big thing that's encountered quite a bit, especially when you have topography issues and issues with the terrain in your forest type, is that there's systematic variation. Now this graph shows a pretty extreme version of this, but imagine you took sampling points every, say, 50 meters apart, but there's a river in between each of those sampling points. Well, if you're only sampling basically on top of the hill, you're not getting and you're not capturing any of the trees that are happening in the river valley down below. And so that's an important thing to recognize as you think about integrating systematic sampling into your design. I won't go into too much of the mathematics behind these common sampling designs, but I will say that the variability is often a problem when you're talking about systematic sampling. It's a lot more difficult to quantify relative to simple random sampling. So I'll kind of leave it at that, and maybe we can touch on that again later here today. So those are really some common ways, some design frameworks we can think about in terms of sampling. But when it comes to doing this in the forest, we need to think about different ways and different types of, in our case, forest inventory plots to measure some of these certain kinds of attributes. And so a common way that people do, probably the most common across the world, are these fixed area plots. And so this is just one example. So this researcher looks like he's measuring maybe the cover of different grasses in this. This looks like a 1/2 square meter by a 1/2 square meter plot. And so this is a fixed area plot. It's of known distance. It's square in design, and they're calculating things like this all the time. And so these fixed area plots are really, really useful in timber resources, non-timber resources, and they're really good for permanent sample plots. And so again, that idea, if you wanted to visit a plot again to measure the growth of the same trees on that plot, people use fixed area plots to do that. And it's very widely used for that because they know they can go back to the same point and measure the same trees over time. And that gives them a really good estimate of the growth and ultimately the yield and volume of many of those trees. And so these permanent sample plots are a good use of some of these fixed area plots that we come across in forestry. Now, it should be noted too that these trees are sampled based on how abundant they are or how frequent they are. And so we say that samples of trees are collected based on the probability proportional to their frequency. And so with a fixed area design, you basically count every tree that you encounter within that fixed area plot. And these fixed area plots can take a lot of different shapes. And so there's really no single way to do it. They could be circles, they could be squares, they could be rectangles, lots of different ways to do these. What we use a lot in the United States are these circular plots. They work really well. Basically, you know, in this plot is in the center, and then you measure out, say, every 20 meters or 10 meters, whatever your sampling intensity is, and that's how you measure. Now, in other areas of the world, especially in more tropical places, tropics tend to use more of these rectangular or square designs. And that's because the vegetation is often more of a problem when you're encountering it compared to temperate forests. And I know a lot of people, I was working with some folks in Mexico on a project many years ago, but the reason that they chose some of these square designs for their plots was because it was easier to outline and define where the boundaries were, rather than these circular designs where you can imagine it can be pretty tough. And actually what they were doing was they were actually making small lines, basically with machetes, going through the forest to outline these boundaries for these square designs. And so it's easier to do that in a square design than a circular design when you're trying to make those boundaries with a machete. So an interesting fact there. And many of these fixed area plots can also be single plots. You have one plot, you measure it, move on to the next plot. They can be clustered. That is, you can have one plot and then offset to that a short distance. You could have another plot and maybe in some systematic way. Or they could be nested. And these nested plot designs are really common in forestry, particularly for some of the research applications and for some of the permanent sample plots that we often rely on. And so this graph is showing an experimental forest that's here in Maine that did just this with this nested design. And so here's the plot center. You can see that there are different plots here, and they measure different size trees on these different size plots. And so as an example, in this 1/5 acre plot, they're going to measure all trees greater than 4.5 inches in diameter at breast height, and that radius is 52.7 feet. And so they're going to be measuring those big trees on a big plot. Now, trees smaller than that, that is trees 2.5 to 4.5 inches, they'll measure on a 1/20th acre plot. And so that's kind of the circle within a circle. And with the idea there being, if you have smaller trees, you want to measure them on a smaller plot because you don't want to be counting hundreds and hundreds of trees on every plot. And then trees less than 2.5 inches, but greater than 0.5 inches in diameter are measured on an even smaller plot, or a 1/50th of an acre plot within all of those. And so you can kind of see the smaller the tree, the smaller the plot we measure them on, getting us to these millacre regeneration plots, which are 1/100th of an acre. And these are L seedlings that are less than 0.5 inches in diameter at breast height. And so all of this happens, there's just one plot center for all of these, but they're nested in a framework that allows us to sample them efficiently based on the size of those trees that we might find in the forest. You might be interested in saying, okay, well, these fixed area plots are nice, but how do they vary in practice? What size do I need to make my plots be in order to have a good estimate? Because you can imagine, as you increase the size of your plot, you can increase it so much that you can basically measure the entire forest if you have a big enough plot. But you don't want to measure it so small that you're not capturing a lot of the variability across the forest. And so this was a study that was done, this was in the central mountainous region here on the east coast of the United States. And what they did was they measured different plot sizes in this, primarily this large trees, large hardwood tree forest. And they basically calculated the common forest inventory metrics, like the number of trees per acre, the basal area per acre, the board foot volume per acre, and then the number of trees that they counted. And they had a look at that. Now, what you can see is that there's a lot of difference when you move from a plot that's very, very small to one that's, say, 0.1 acres in size. And so as you do that, you basically get fewer trees per acre there. You get basically a smaller basal area per acre and a smaller volume per acre. But the difference between a plot that's 0.1 acres in size and 0.3 acres in size is very minimal. And so you're basically getting the same number of trees, you're getting the same basal area and volume than you are with a 0.1 acre size plot and a 0.3 acre size plot. And so it goes to show you that if you look at some of the things like the coefficient of variation, which is just a measure of how variable your unit of measure is. So they have these for the three attributes for a board foot volume, basal area, and trees per acre. The coefficient of variation changes little when you go from this 0.1 to 0.3 size. Now it still goes down. You can kind of see how the line is going down, but it doesn't go down as much as, say, between a very, very small plot and a plot that's 0.1 acres in size. And so this is all to say that there is a sweet spot, you might say, in choosing the plot size that works for your forest type if you're going to implement fixed area plots in your forest inventory. And so this is just an example of fixed area sampling, fixed area plot. And so in this case, this is pretty intuitive, just kind of a review, but you have a sample point. This is your plot center. And in this plot, you would have three plots that you measure. So here's a large tree, here's a small tree, here's another large tree. So that's fixed area sampling and design. We're sampling with probability proportional to how abundant or how frequent the trees are in the landscape. Now, to introduce another point, or another plot way, another way to measure plots through a sampling framework is called point sampling. Now, instead of fixed area plot sampling where we have one size plot, imagine that every single tree has a different size plot associated with it. Now that might look something like this. So if you have a look at this big tree here, it has a relatively large plot surrounding it because it's a large tree. However, if you have a look at a tree that's located here, this is a small tree and it has a smaller plot associated with it. And so this is point sampling, or sometimes people call it prism sampling, or point cruising. This is a method that can basically get you the same kinds of information that fixed area plot sampling can do. But in this case, we do it with this idea that each tree is a plot instead of you have one plot and you measure each tree within it. And so we call this point sampling. The big difference with point sampling is it samples trees with probability proportional to their size. And so in the case of what we just looked at, it was really the size of those trees or the diameter of those trees, with a tree with a larger diameter being more likely to be selected. And that makes sense from a forestry perspective, because many of the forest resources that we've done historically are based on trying to understand the volume in a tree, or how much forest resources or forest products might be able to come from those trees. And so it makes sense if we weight our sampling toward those trees that have more timber in them or more forest resources, so that we might be able to say something about how much volume or biomass might be in that tree. There's a lot of interesting mathematics behind this approach, but in general, it projects a horizontal sighting angle at diameter for every tree from one plot center. And so the awesome thing here is that you don't need to go up to the tree and measure its diameter to calculate the basal area of a stand. And so it really uses some awesome mathematics. I'm happy to chat more about this, but it's a great way, one of the most common ways that people sample to calculate some of our core forestry information that we collect on a daily basis. So this idea of point sampling is really common. And here's how it's done. And so you need what is called an angle gauge, some way to look at that. So go back to that sighting angle. We need some angle to basically do that when you're in the woods. And so these are prisms. You can buy these for fairly cheap. And what they do is they basically refract the light. And so you can basically sample trees that are in and forget about the trees that aren't included in your sample. And so these are two prisms here. This is an angle gauge on a wire. And so you hold the wire kind of a set distance from your eye, and then you point that angle gauge to the tree. And you can see it has kind of these different diameters within here. And so your trees can be sampled as being either a tree that you sample or not, based on where it falls in here. And then this is a really interesting German tool, the reloscope, that some people still use today, that helps to measure trees using this idea of refracted light and some of these different sighting angles. This tool is still quite expensive. Not a lot of foresters have these, but they're still widely used. And a lot of the newer technologies you might see with like laser pointers and things like that use some of the concepts from this reloscope to be able to sample trees in the forest. This is just an idea of sampling. Many of you maybe have done this in the field or have seen this approach, but the tree is in. If the angle of it, the refracted angle of it, the offset portion of the tree is still touching the main central bole of the tree. And so in this case, you would tally this tree. But if the offsetted piece of the bole is outside of the main stem of the tree, you do not tally this tree. And then you have borderline trees where, oh, it seems like, you know, the width of the tree, it's the same as, you know, it's just touching there. And so in this case, you could tally it, but you should really check because we know, depending on how the size of your prism that you're using, you really would know. You would have to measure the diameter of this tree with the diameter tape, but you would be able to tell based on how far away you are from the tree and the diameter of that tree, whether or not you should sample it or not. And so you can imagine, like I said, this is a really neat approach because you don't have to really measure the diameters of trees to understand what the basal area is of a stand. And so it's kind of a more lazy way to do it because you could basically stand in plot center and get all the information you need without having to walk around as much. So there are different basal area factors to use. That a BAF is a basal area factor, and these are in English units. Again, my apologies for that, but you basically choose a different size prism based on the size of the trees in your stand. And so if you have a really, really small stand, like this stand is going through severe self-thinning, it looks like all the trees are, gosh, less than 10 centimeters in size each, probably less than 5 centimeters based on the trees that I'm seeing here. You want to use a very, very small BAF because you don't want to use a big one that will count all of these small trees. But in a stand where you have lots of large trees, and so this is a stand in Maine with lots of eastern white pine trees, you want to use a larger BAF that way because you want to be able to select, because these trees are spaced out so much more, you want to be able to select a certain number of trees as a part of your sample. So to kind of recap those two approaches, the fixed area plots, they're really easy to install. Again, they sample trees with a probability proportional to how frequent they are. They're good for repeated measurements. They're also great, we didn't talk about this, but if you wanted to determine ingrowth, so those would be the trees that you're not seeing today, but grow into a plot sometime in the future, it's good for that. And then if you're using like these kinds of fixed area plots in a permanent sample design, well, if you're revisiting it more than once, you could get a sense of which trees die. And so you have a sense of what the tree mortality is as well. It can be pretty intensive in terms of time. It can be sensitive to edge effects. We haven't talked about that much, but when you're in the field, those boundaries of your plot matter a lot more. And then again, each tree has an equal probability of being sampled. For the variable radius plots or the point sampling, another term for it, it's fast, it's easy, and it's going to favor those larger trees because it samples with probability proportional to size. but you need to know kind of which size prism or which basal area factor, BAF, you want to use. And then you might want to be known that if you miss one tree in your sample, it's going to have a much bigger impact with this variable radius plot design than it would because compared to the fixed area plot, just because it's a much more different sampling design that relies more on the size of a tree as being selected rather than the abundance or the frequency of a tree being selected. So then I want to talk and just kind of finish up some of this, some of these slides on sampling to talk about the importance of stratification. And so the goal of stratification is to minimize the variance within a stratum to obtain a narrower confidence interval with the same sample size. And so what I show here on the right, imagine this is a forest with different strata. And so we have 6 different strata here, labeled 1 through 6. Imagine these are different stands. They're not of the same species or not of the same age, or something like that. There are lots of things that you can stratify by. Typically, it's stands when we do this in forestry. And those stands are often designated by the age of the trees, the species, the soils, the kind of topography environment, and some other things. And so lots of different ways to stratify these stands. And the goal of stratification is that it reduces the overall and the within stand variability. And so again, with the goal of trying to quantify and measure the same number of samples or even fewer samples to get a better estimate of variability. So imagine we took 18 sample points in a fixed area design using simple random sampling. And so this is what we might get. If we look at some attribute, say this could really be anything, but say this is the volume of a forest. Well, we know that we have a distribution. And so this plot here in the northwest corner is going to look differently than this plot here in the southeast corner. And so we have a distribution of the volumes, in this case, of these plots doing simple random sampling. But what stratified random sampling does is it takes into account these are different strata. And so we know that we have different variability within that strata. And so if you have a look at our simple random sample variance, what we get with stratification is a much narrower distribution. We get that obviously for each strata. Imagine these are different stands. We get that for each stand. But what the cool thing is that we also get it when we combine all of those different strata into one. And so even for the stratified variance compared to the simple random sample, we get a much narrower distribution there. And so that's really awesome because it means that we can basically use these same data that we collected. And if we do stratification, we can basically narrow our confidence interval. And everyone likes a more narrow confidence interval when you report up to your supervisor or other people that are in charge of the project that you're working on. And so that's kind of the slides. And I wanted to show some application of this and how these sampling designs are used and some of the things that are going on. And so I'll switch over to R in a moment, but I guess I will just take a stop quick and just see if there are any questions either in the chat or otherwise, and just pause for a minute if anyone has a question. All right, well, not seeing any, but again, if you do have a question, type them into chat. I'm sure we can get to them here fairly quickly. So I just want to talk a little bit about the data and the R package that I'll step through. And so what we're seeing here is the forestsamplr package. Now, what I really love about R is that anyone can write a package and make it available to other users that can go and use that package and then also develop more as a part of that package. And so this is one that I've used that really focuses on these estimates of sampling designs and how they're used in natural resources. And so this is an R package that estimates population parameters from these common sampling designs. It was developed by a program or a company called NCX, and then you can see the link there. It's available on GitHub if you wanted to download it. And so the goal is to using stratification. In our case, we want to determine the optimal number of sample plots to sample given our set of forest conditions. And so the data I'm going to talk about, this is that experimental forest that's just up the road from where I live now, called the Penobscot Experimental Forest here in Maine. And this forest is unique because it has lots of species here. So we have lots of conifers, lots of hardwood species. And this is a photo in fall where you can see these are mostly fir and spruce trees growing. You can see the green canopies of. But the trees that are changing color are mostly probably maples, birches, and other hardwoods that are mixed in. And so this is a mixed species stand. There's a lot of variability when we look at things like basal area and volume from, say, one plot to the next. And so just to give you a sense of what the data look like. Now, here's how the data were collected. This is basically a systematic sample. And so this is one stand. I think this is, yeah, it says 31 acres stand here. And so the way the data were collected were in these lines systematically. And so a field crew will start measuring plot 1, traverse, in the same direction and measure plots, and they kind of set these lines up systematically throughout the stand as they go in and measure. And so, so that's kind of the background about the data set that we'll use, that will go into R. And then again, I'll put a link in the chat. All of those messages or all of those resources are available in that GitHub repository, which I'll navigate to right now. So this is GitHub. I love GitHub. So GitHub is kind of like a social platform for coders and developers. And so you can basically share any code you've written, any data sets you have, other documents. It's a really awesome way to share and collaborate with others on coding. And so I also tend to use it just as in many ways, as a repository, like sharing files like this. It's really easy to share with others. That way you don't have to email back and forth with large data files and things like that. So so here are the files I'm basically working through today. So what I'm going to do, I have this open in my R screen, but I'm going to look at this stratify.rmd file. And so if you have R on your computer, you should be able to open up R and then open up this stratify.rmd to kind of follow along. So I'll open up R now. And you can kind of see how things look here. I am going to make this just a little bit larger. I never really know how things come across on Zoom, but hopefully you all can see that and it's at least a good enough quality. I use step back. I use the dark mode in R. So I use actually R Studio, which is just and they call it an integrated development environment to access R. And so R is really like the workhorse that does all the work, but R Studio is just the way that makes it easier to interact with R. And so that's just what I'm doing. And I turn on the dark mode just because it's easier on my eyes, because some days I work with R quite a bit, and I find that the darker setting tends to work easier on my eyes. So that's what you're seeing here. Another thing I wanted to mention, nope, I need to open up the other file, not the tidy regression file is the one we'll do in the next session. But the stratified.rmd file is the one that does the stratification. So I'll open up that one. And you might notice something, I don't think everyone does this, but I really like these kinds of files. This .rmd stands for R Markdown. And so what I really like about this is that you can basically write R code but then you can output your code that you write into different kinds of formats. I won't do it now, but if you go up here in RStudio in the knit menu, you see there are a couple options to do here. So you can knit this to HTML, or you can knit it to PDF or to Word. And what I like about that is that you can basically write R code plus text with your figures and with tables and things like that. And after you're done with it, it's not just an R file, but you can actually turn that R file into something that you can share with others, like a Word document or a PDF. And so I find that that's really helpful, especially in collaborating with others. They don't have to actually read my code. If it's another person I know that does coding and that is familiar with code, I might just send them the R code. But I work with a lot of people and a lot of companies that say, well, we don't need to know all the coding you do to get the answer. We just want the answer. And so with that, I often will write my code and then use this knitting feature to save it as a PDF or as a Word document. And so just some background there about some of these different data files. So what I'm going to first do is, and somehow I switched over to the tidy regression, but I'll go back over to the stratification example. What I'm going to do is really what you do first whenever you're working in R is you want to read in the libraries that you're going to use. And so that's what I'll do here when you see these different libraries I use. The first one, G Sheet. It turns out I like to read in a lot of data from Google Sheets. And so that's what you're seeing here. That's the library that does that. DevTools is a package that helps to get some of these other different packages installed in your machine. And then Tidyverse, I think if there's one package to install in R, in my opinion, it's the Tidyverse, because the Tidyverse is really a suite of packages that makes it easier to work with, manipulate, and do things with data. And so I'll install these here. And then I'll go over here, there's a little play button here where you can have these different chunks of code. And so I'll hit play there, and you can see the code is running down here in R, for those of you not familiar with this. As we start to add data sets and we start to get some results, you'll see this environment window will start to open up and start to populate with different things. And then down here, you'll see plots. Eventually, when we get to plotting some of the data, you'll see those plots start to appear over here. So just to give you a sense about kind of what we're doing, we tend to write all the code in what we call the editor window in the top left. It's all output into the console, and then the environment kind of stores everything, and then the plots kind of shows everything once we're done seeing it. And so now we want to read in the forestsamplr package. Now the forestsamplr package, if you haven't installed it yet, I've got the code there. And I just commented it out by putting a hashtag there. But you can remove that hashtag and you can kind of see how the code, now it looks like it's going to run if I click that. But in that case, I know I've already got it installed, so I don't need to install it twice. So I'll put the hashtag there to keep it from running. But I do want to run the library forestsamplr is the name of the package. So I click run, and you can see it loaded really quickly. And that's nice. So then I'm going to go down to the next chunk, and it says it's going to read in data from the Penobscot Experimental Forest. Then I have the link there if you wanted to learn more about the forest. And we'll use data from forest stands or management units that are managed silviculturally. One is on a 5-year selection interval, and so they're going in every 5 years and selecting individual trees or groups of trees. And then one does that every 5 years, one every 10 years. And so some differences there. And so I'm going to read in the data using, and I'm going to call this data set, I'm going to call it tree. And this G Sheet 2 table is from that Google Sheets package. And so if you were to copy and paste this URL, you should be able to see those data that I'm downloading. And I also put them in the GitHub repository. So you have a couple of different ways to access the data. And then I'm just going to do some subsetting here. The data set's kind of big if you look at it. But again, I only want those 4 different stands, 2 measured on a 5-year selection interval and the 2 measured on a 10-year selection interval. And so I'll go ahead and click that. And again, don't feel like you need to follow along completely as I walk through this. But again, remember those resources are available on the GitHub repository if you wanted to have a look. So we've got the data in, so that's good. So it looks like it didn't pop up any errors over here. And you can see our environment window also populated with something. So that's good. That means our data is in. And so what you can do is you can actually go ahead and open this. And when you click on the tree data set, you can see the data here. And so you can see a couple of the key things that we're going to look at are things like the DBH. And so these are in inches, the diameter breast height in inches. So you can see that there. And then there's some other things. So here's the management unit number, here's the plot number, and some of these other attributes as well. So there are the data. It opens up as a separate tab. I like that. I work a lot in Excel and a lot of spreadsheets, so I like to see the data kind of in this tabular format often. So our next step is we have 68 plots that were sampled. Let's assume that they were sampled randomly across these forest stands, representing a simple random sample. What we can first do is summarize the data to calculate the basal area. And so to do that, I'm going to use the tree data set. I'm going to make a data set called plot. And I'm going to group it by the management unit or the stand and the plot number. And so within each management unit, I have multiple plots that I've measured. And I'm going to calculate the basal area. And so that's what I do on this line. And to calculate the basal area, and again, this is the English way to do it, not the metric way. And so the results will be in square feet per acre. But I sum the diameters and I multiply them, and I multiply them by the expansion factor, and that's how I get the basal area. And then I'm just going to do some other things. I'm going to use the mutate function to add a couple of other columns to the data. I'm going to say, well, I want a value called stratum, which is basically the management unit or the stand. And so I'll add that. And then I want something called treatment. So I know that, if it's from the 5-year selection or the 10-year selection treatment. So that's what I'll do there. And then I'll summarize the data by the stand or the management unit. And so I'll group by the stratum, and then I want the number of plots, the average basal area, and the standard deviation of basal area. And so I can click run on that. And then you can see over here in our environment, it made those new data sets. And so if I open up the plot data set and have a look, here's my management unit, here's my plot, and here's my basal area. So these are in square feet per acre. Again, sorry, you might be more familiar with square meters per hectare is what most of the people use across the world. But in the United States, we want to be different from the rest of the world, I guess. So we tend to use these values of basal area in square feet per acre. So if you scroll through the data set, you can see, oh, that's great. I know there are 68 plots that were measured. I have 68 different rows in the data set. So I feel good with working with this data set moving forward. So next thing is I'm going to visualize the data. And so my favorite way to visualize data in R is the ggplot package. What I'm going to do is I'm going to use the plot data set. I want to group these on the x-axis by stratum. I want to plot the basal area. And I want to fill them. You'll see I get different colors for different treatments. And so that'll be good to see. And I want to make a violin plot. So this genome violin allows me to make a violin plot, and we'll see what those look like in a minute. And then I can add some labels here. And so on the X, I want to call this stand ID. And on the Y, I want to say basal area, and then my units there. So I'll click run. And then you can see in the bottom right what happens. I'm going to make this bigger just in the short term to really see this graph. So here are our violin plots. And so for our 4 different stands, we have the distribution of basal area in square feet per acre for each of those stands. And so you can see, in this case, the 2 5-year selections, and then the 2 10-year selections. And so it looks like if I look at stand 16, I can see, oh, that's kind of well or normally distributed for the most part. But if you look at a stand like stand 20, it's very variable. It looks like there's a peak here at somewhere around 160 or 150 square feet of basal area. But it looks like there's at least a few plots that are quite larger than the rest. And so I like these violin plots because you can see how variable your data are relative to other things. Okay, so next up, we want to, again, assuming that simple random sample, the population mean of basal area can be calculated using summarize all SRS. And that's a function directly from this forestsamplr package. And so you can basically calculate what the variability is there. And so that's what I'm going to do here. I'm going to do it on the plot data set, and my attribute I want to know the variability of is basal area. And so I can hit run there. And you can see in the window, it outputs the mean, the variance, standard error, and then the upper and lower confidence intervals. And so that's pretty nice. And so this, by default, is the 95% confidence interval. And so we might be interested in changing that to see, well, what does a 66% confidence interval look like? And so using this handy function from the forestsamplr package, we can basically change our confidence interval by adding this, desired confidence equals 0.66. And so if we hit run on that, we can see the output here. Now have a look at this. The mean and the variance don't change at all. And that makes sense. But what does change are some of the confidence intervals. And so by choosing a lower confidence interval, like 66% instead of 95%, we get a smaller limit. So you can see the values are different here. And so the 95%, it goes from about 152 to 168, whereas the 66% goes from 156 to 164. And so it's a narrower interval because you're less confident about the result. And so we can begin to change that. We could go ahead, if we wanted a 80% interval, we could enter that here and hit run. And you can see how these confidence limits change based on how we change them in the package or in the function there. Our next step, we're going to make a new data set called stratum tab or stratum table. And so for stratified random sampling, you need to know how big the strata are, or how big your stands are, to understand how some of this mathematic works. And so all I'm going to do here is enter the acres of each of those stands. And I know this because I'm familiar with the data, but you likely might have this for your own stand or your own forest that you're working in. So I'm going to hit run there. And then I'm going to scroll down, and you can see what I'm doing here. The population mean can be calculated using this summarize stratified function, which requires that stratum table data set that contains the area of every stand, and then the output is provided for each stand. And so that's a handy thing for us to know. And so again, I'm going to use the plot data set. I'm interested in the basal area. And that stratum table has all those sizes of the stands, so it can stratify by doing that. And so I'm going to hit run, and you can see the output here on bottom right. So now what it's done is it's calculated all these by stand. And so you can see the means now for each of the different strata are different. The variances are different. And of course, there's a different number of plots that were measured in every stand. And so what you can see here is that here's the total summary if we were to look at the different strata. The population mean is 166. The standard error is 3.8. And you can see the differences there. And this is the half width of the confidence interval and the percent of that value relative to the confidence interval. So you see that information there. So here's the cool thing. The population mean for the stratified sample is slightly larger than that for the simple random sample. So that's about 166 versus, if we were to scroll back up, 160.45. The standard error, have a look at the standard error for the simple random sample. In this case, it's 3.83. But if we scroll down for the stratified estimate, it's 3.80. And so that's the value and the magic of stratification. We already know if we calculate the within strata variance and we know how large those strata are, we can calculate the variance a bit differently. Now, it turns out that they were sampled in a systematic design, but we could allocate them differently depending on what we wanted to do. And so one of my favorite books, and this is the last example I'll show what we might do with stratification, is this is Forest Measurements. This is a great book by Burkhart, Avery, and Bullock. And if you look at what they talk, when they talk about sampling in this book, they talk a lot about stratification, and they talk about different ways that you can allocate the number of plots based on how many plots you have. And so they present two approaches, basically what they call a proportional allocation. And that's where you say, well, if you have 150 plots, in our case, you can proportionally measure them. You measure more plots in the stands that are larger in size. That makes sense. You kind of divvy them up by the size of the stands. Or you can have what they call the optimal allocation, where they try to optimize the number of plots you take in a certain stand based on the variability in that stand. And so both are ways that you could sample in our case. And so let's have a look. And what I'm going to do, what I do here is I write a function to calculate the proportion to allocate. And then what I do is I say, okay, I'm going to make a new variable called number of proportions, or the number of plots through the proportional allocation method to measure. And I'm going to add that in the stratum table data set. And so I know how many acres are in each stratum. I enter that here. I know the total acres across the unit. And I have 150 sample plots. And so this example says, well, if we have enough money and enough time to measure 150 stands, how would we measure them? In what stands would we measure them? And so I'll hit run here. And you can see here, it gives for each stratum, it has the size of them. And then it has the number of plots you should take if we wanted to sample 150 total within each of those different values, for each of those different stratum. And so you can see, well, it makes sense in our largest stratum, in stratum 12, that's 31 acres in size, we need to measure 49 plots, but in stratum 16, that's just 16 acres, we can measure 25 plots. So pretty straightforward there. But what if we compare that to the optimal allocation? So again, the optimal allocation is going to distribute those 150 field plots that we want to measure to the smallest amount of variability as possible. So if there's one stratum that doesn't have a lot of variability associated with it, you don't need to measure as many plots there because there's not much variability going on from one plot to the other. Where you do want to measure more of your plots are in those stands that have a lot more variability, so you can try to capture more of that with more plots. And so what I do here is I just kind of merge some data sets together, and then I calculate the areas here. And then same thing with the second chunk here of code. I'm going to calculate a function, write a function that calculates this optimal allocation method. And then I'm going to add it to the stratum table. Again, basically saying I have 150 plots and I want to allocate them. And then I'm just going to output to see what the data set looks like. So you can see here in the lower right. So what happens? If we compare the optimal allocation versus the proportional, you can see they're not the same. And so that's interesting. And so as an example, let's have a look at the one with the lowest variance or the lowest standard deviation. It turns out to be this one stratum 12, which has a standard deviation of 25 square feet of basal area. We would measure proportionally, if given the size of the stand, we would have to measure 49 plots. But because it's the lowest variable stand, if we optimize our sampling, we only have to measure 45 plots there. Now we're going to have to measure plots somewhere else if we want to get to that 150 number. And as one example, we might want to measure more plots in stratum 9 because that stratum has the highest variability of about 32 square feet of basal area. It's not one of the largest stratum, but the optimization methods tells us to measure more plots there because it's much more variable relative to the other stands. And so this is just an example of how we might use R and one of these packages to really get a sense of how we can understand and how we can interpret some of the values that we're seeing. And so hopefully this has been useful to understand just one application of R. Again, don't feel like you have to go through everything line by line with me. All the resources are there and available to you, but I thought I would show an example of that and people that I work with, the kinds of things that I might do on a regular basis. So with that, I think I'll take a stop and check to see if there are any questions before we take just a 5-minute break or so.
Sorry, can I ask you, please? Thank you so much, Matt, for your insightful presentation. I would like just to ask you one question about the stratified process, which is, I believe, the most used process in forest sampling, given that the growth conditions are usually aggregated in one place. Allocating the plots in different strata, this implies that we have a preliminary idea about the variation within those variation of basal area, variation of diameter, etc. in each strata. And usually we use the pre-sampling process before initiating the sampling itself in order to obtain a preliminary idea about this variation. What do you suggest, or which number, numerically, which number do you suggest to take number of plots to inventory in each strata for the preliminary sampling process? Thank you so much.
Yeah, thanks for that question. It's a good question because like I said earlier, some of these sampling strategies rely on us to know something about the forest even before we go out and measure, a new set of forest inventory plots. And so oftentimes there is available some data, not necessarily about the same forest that you're working in, but it could be from a similar forest or a forest you measured of similar design recently. And for that, to get some of those data, if you don't have any available, I always suggest people do like a pilot study where, if you have like 1 day to spend in the forest in the area that you're interested in working in, to collect some plots to get a sense of what the stands look like, that would be really, really valuable information because you could begin to understand what those variabilities are, as you go from one stand to another. As an example, I work a lot in forests here in the eastern United States, and I know that if forests are these natural mixed species stands, my coefficient of variation, if I look at volume or basal area or some of these other attributes, it's going to be about 100%. That's pretty high. But if I'm working in a plantation where trees are planted in rows and trees are planted in a pretty optimized way, I know the coefficient of variation is going to be about 30%. Give or take, it's not always going to be those numbers by any means. But I think if you have the opportunity to collect pilot data where you spend, even just half a day or a day collecting information, that can help a lot in terms of identifying some of the numbers that you might use when it comes into some of these stratification estimates and similar things.
Thank you. Thank you.
Yeah. Other questions before we take a break?
Sorry, I wrote on the chat box what you meant by ggplots.
Oh, is there something in the chat? Yeah, I haven't. Yeah, ggplot is Yeah, it's a way to make graphs in R. And so it uses the principles of what's called the tidyverse. So the GG in ggplot is an abbreviation for the grammar of graphics, is how it's called. And so, yeah, so the ggplot, it's really just it's one function that's used in R, but it's a really powerful function because it allows you to create many different kinds of graphs that you might be able to say something about. And so, yeah, I would encourage you, if you want to learn more, especially the visualizing data in R, to have a look at ggplot and what it can do for you and your analyses. All right, well, I could use a quick water break, I know. Maybe let's take 5 minutes. And I don't know what time, I know many of us are in different time zones, but let's meet again at 20 after the hour. And then, so 20 after hour, for me, that would be 12:20 p.m., but for you, it might be something different. So let's just take 5 minutes and then come back and we can talk a little bit more statistics. Thanks, everyone.